Thermo Review number 1. So we've got a table up here, we've got some substances, and they seem to relate to this reaction. This looks like this is the metabolism of glucose, and they tell us that the standard enthalpy change, delta H, for the reaction is negative 2801. So we know right away that it's an exothermic reaction. It's going to give off heat. Alright, part A. Calculate the standard entropy change, delta S, for the oxidation of glucose. Well, we have information up here about the entropy values. You remember, one of the differences, as long as we're talking about general concepts, is you might think if this was a delta H table, that this one would have a delta H at 0, because all elements in their standard form are 0. But you remember, entropies are never 0. All compounds have some sort of entropy. How we calculate it, though, is definitely going to be a sum of the products minus reactants approach. And so that's what I'm going to set up. Alright, so we've got set up products minus reactants. This one right here, the reason it's 6 is because that represents the CO2, this represents the H2O, and the coefficient in front of H2O was 6, just like in front of CO2 it was 6. So there are the products, and I'm adding them together, minus the reactants, and it's 6, so this must be O2. Times its entropy, and this last one must be the C6H12O6. And when we calculate them, our delta S is going to come out to be 259. And we got to think of what the units are, and remember, entropy is the one that's different. Delta G and delta H, generally when you're looking at them in tables, they're kilojoules per mole. Delta S generally is not, and you can see it up here, it's joules per mole. Oh, joules per mole, Kelvin, I should say. In part B, they want to know, they want us to calculate the standard free energy change, delta G, for the reaction at 298. Well, we know delta H from up here, and we just calculated delta S. The delta S was 259 joules per Kelvin. And so we can calculate it using this equation. When I plug in the values, it's going to be negative 2801 kilojoules for delta H minus our temperature, which is 298, okay, times our delta S. But I don't want to do 259. You can probably guess why. It's in joules, and the rest of the stuff is in kilojoules. So we want to do 0.259 kilojoules per Kelvin. And you notice the kelvins cancel, one on top here and one on bottom over there, and we can calculate our delta G. And it looks like we're going to get negative 2880, and we got to think about units. Well, we had all of these in kilojoules, so it's probably reasonable to say kilojoules, and usually it is per mole. Part C could be worded a little bit better, but we get the idea. It says, using the axis below, draw an energy profile for the reaction. Now, when they leave it vague and they say energy, you remember most of these kind of plots where they have like curves, we tend to be doing delta H. When they leave it open like that, you technically could be doing free energy, but it turns out in this case it doesn't make a difference. And the reason is because the delta H is negative, and so was the delta G. The delta G was actually not very far off of this number. They were both pretty similar. So either way, it's not going to make a difference. So what we have to think about is, if this line is for the reactants, then where do we put the finishing line for the products? And it's a reaction that's giving off energy. So the question is, are the products going to be higher in energy, or are the products going to be lower in energy? And if it's not absorbing, this would be absorbing energy. That's not what it's going to look like. It's definitely going to be releasing energy. So it should look more like that. And while we're here, let's just be good about it and label what I think they want, which is from here to there is the delta H of the reaction. In part D, they want to know how much energy is given off by the oxidation of 1 gram of glucose. So there's glucose. We're wondering how much heat is given off by 1 gram. Well, we know that the amount of heat given off is negative 2,801 kilojoules. So you might wonder, why is that not the answer? But you remember, this is for a mole of glucose, and we're not doing a mole here. We're doing much less than a mole. So when we do this, when we're converting energy to amounts, it's always good to have an energy conversion factor. And in this case, our energy conversion factor is going to be 1 mole of this C6H12O6 is equal to negative 2,801 kilojoules. And you remember, in these energy conversion factors, the number is not always 1, it's just 1 in this case because that's what it was in the balanced equation. If they'd been asking about oxygen, it would have been 6 moles of oxygen equals negative 2,801 kilojoules. So now that we have our energy conversion factor, it really is just a unit conversion problem. So we have 1 gram of glucose, which I'm going to abbreviate as GLU, and we're going to convert that from grams to moles. And so we're going to need to know the molar mass of glucose. And if I add it up really quick in my head, it comes out to be 180. Alright, I cheated. I looked on a sheet. But hopefully when you add them up, it comes out to be 180. And then those will cancel. And then we got to use our energy conversion factor. So 1 mole of that glucose to negative 2,801 kilojoules. Everything cancels, and our answer is going to come out in kilojoules, and we get 15.6 kilojoules.